Welcome back. This lecture is going to cover Earth's orbit, tides, seasons, and irradiance. So let's get started. This lecture has a lot to do with astronomy, so I wanted to start off with a quote by Albert Einstein. The intellectual resources with which the development of modern technology has become possible have been derived mostly from the observations of the stars. I think this is really true. We have learned so much by being curious about the natural world, including the stars, universe, and so on. And I've included a really beautiful image of a barred spiral galaxy taken by the Hubble Space Telescope. Let's talk about some of the astronomical factors for habitability. Obviously, our planet meets these requirements as we are living on it. A lot of planets don't, but some do, and that is where we are focusing our attention when we search for extraterrestrial life. The requirements for life are as follows. Life needs specific stable temperature regimes. Most of the universe is either way too cold or way too hot, but not our Earth. The warmth for Earth is provided by Earth's star, the Sun, and the Earth exists in what is called the Goldilocks zone. Its orbit around the Sun makes it so it isn't too hot and it isn't too cold. Life also needs liquid water. Water can only exist within certain temperatures and pressures, and so a habitable planet has to have these temperatures and pressures. Life also needs long-term stability. Life needed more than 3.5 billion years to evolve to its present state on this planet. So ultimately, whether a planet is habitable for life, as we know it, depends very strongly on some basic astronomical factors. Properties of the planet's star, for Earth that's the Sun, including its size and temperature, longevity, and so on, are all very important. The details of the planet's orbit also matter. This is the distance to the Sun, seasons, and so on. Finally, the composition and size of the planet and presence and properties of its atmosphere are also important. Here is a view of the planets in the same solar system as us. All of these planets orbit around the Sun, but at different distances away from the Sun. The planets are different sizes and compositions too, but we aren't going to talk about that. We are going to focus on Earth. The Earth is the third planet from the Sun. The distance from Earth to the Sun is enormous, about 150 million kilometers, but we call it one astronomical unit. Our solar system is in the Milky Way galaxy. The Milky Way galaxy includes 100 to 400 billion stars. The name Milky Way describes the galaxy's appearance from Earth, a hazy band of light seen in the night sky, formed from stars that cannot be individually distinguished by the naked eye. Just in case you weren't clear on the definition of a galaxy is a gravitationally bound system of stars, stellar remnants, interstellar gas, dust, and dark matter. Estimates for the number of galaxies in the universe vary widely, but 100 billion to 200 billion is a widely accepted range. Here are some basic principles regarding Earth and its orbit around our Sun. The Earth revolves around the Sun once every 365 days, so once a year. The revolution path is kind of a circle, more of an oval. This is also known as an elliptical orbit. The plane of the orbit is called the ecliptic, a similar term for a related but different thing. The elliptic is the shape of the orbit, and the ecliptic is the plane of the Earth's orbit. The Earth also spins on its axis. This is called Earth's rotation. Earth rotates once every 24 hours. Earth's rotation creates the day-night cycles we experience. The spin axis, shown in red on the image, determines the North Pole, the South Pole, and the equator. You will also have to know what the circle of illumination is. The circle of illumination is the half of the Earth, the half of the planet, that is illuminated by the Sun at any given time. Half of the Earth is illuminated because solar rays from the Sun all arrive parallel to one another. They don't really wrap around the planet, so half of the Earth is facing the Sun at any point in time, and every part of the planet that is facing the Sun is experiencing daytime. The other half experiences nighttime. Even though solar rays come to Earth parallel, the Earth is a sphere, and so its surface presents all sorts of angles to the Sun's rays. This is a main factor in why the equator is hotter than the poles. We will talk more about this later in the lecture. You should also know that the Earth's axis of rotation is tilted with respect to the ecliptic, and this causes Earth's seasons. The details of Earth's orbit and orbital motion are described by Kepler's laws of planetary motion. We'll talk more about that later in the lecture as well. Now let's talk a little bit more about the Sun. Earth's habitability depends on the Sun and its properties. This is because life on Earth depends almost 100% on radiant energy from the Sun, its heat and light. Photosynthetic organisms take solar energy and turn it into biomass that entire food webs are based on. The sun is a typical second or third generation star. It's about 5 billion years old, and it's in the middle of its lifetime. The mass of the sun is 1.98 times 10 to the 30th kilometers. That's about 330,000 times Earth's mass. Nuclear fusion reactions power the sun. The sun fuses hydrogen into helium. To the right is the sun, as seen by NASA's SDO mission in ultraviolet light. Now that we have introduced the sun, let's talk some more about the day and night cycle on Earth. The day-night cycle is also quite important for Earth's habitability because it stabilizes temperatures on the planet. Day does not get too hot, and night does not get too cold. The Earth rotates once on its axis in 24 hours with respect to the sun. We mentioned that already, but it is really important, so I wanted to say it here again. The exact duration of daylight at any given location depends on the latitude, which we'll define later in the lecture, and season, which is the time of year it is. So-called tidally locked planets have a permanent day side and permanent night side. That creates extremes in climate. One side of the planet is much hotter than the other. You also can't have photosynthetic organisms on the dark side of a tidally locked planet. The moon is actually tidally locked to Earth. The dark side of the moon is the hemisphere which is facing away from Earth. It's not actually any darker than anywhere else on the moon since the moon is illuminated by the sun. The sun and the moon actually create tides on Earth. Remember that the Earth rotates around the sun and the moon rotates around the Earth. The moon takes about 27 days to orbit around the Earth. The moon and the sun affect tidal cycles through their gravitational pulls. When they are overhead, they will pull on the planet and liquid water will be pulled toward them. But the moon is about 2 times more important to tidal height than the sun because it is so much closer to the Earth, despite the fact that it's so much smaller. Spring tides occur when the sun and moon are lined up, at the full moon and the new moon. High tide in a location occurs when the Earth is rotated to line up with the sun and the moon. Neap tides occur when the sun and moon are at 90-degree angles from one another, at the first quarter and the third quarter. High tide in a location occurs when Earth is rotated to line up with the moon. Remember, the moon is 2 times as important as the sun for tidal height. Most places on Earth have 2 high tides and 2 low tides a day. This is because the Earth rotates on its axis once every 24 hours, causing the moon and sun to be overhead and on the opposite side of the planet approximately once a day each. The timing of high tide and low tide will vary depending on where you are on the globe and the positioning of the sun and moon. The time of the month that spring and neap tides occur will also vary depending on where you are on the globe and the positioning of the sun and moon. Now that we are beginning to talk about different locations on Earth, we have to introduce latitude and longitude. To define a position on Earth, we need a coordinate system, essentially a grid. Since the Earth is approximately a sphere, one convenient way to determine a coordinate system is using 2 angles, latitude and longitude, which are measured at the center of the Earth. Latitude lines are the flat lines shown on the globe to the right, while longitude lines are the vertical lines. For those with a background in calculus or geometry, these are analogous to the angles of a spherical coordinate system. Latitude and longitude are typically expressed in degrees and fractions of a degree. In this class, we will focus on latitude because many Earth characteristics depend on latitude. Things like the amount of solar radiation, which affects seasonality and climate, ocean currents, winds, wind patterns, and so on, all depend on latitude or distance from the equator. So let's talk about latitude a little more. The latitude of a point on Earth's surface is the angle between the plane of the equator and the line connecting the point on the surface to the Earth's center. Latitude, together with axial tilt and the seasons, therefore, determines at what angle the Earth's surface will be facing the sun at any particular location. Remember that the poles and equator are defined by the axis of rotation. Parallels are the lines of equal latitude parallel to the equator, also known as circles of latitude. There are lots of different parallels visualized in the image to the right, but an entire latitude-longitude grid is drawn. Here is a flat map with a latitude-longitude grid printed on it. Note that the latitudes that are visualized are 0 degrees north or south latitude, 30 degrees north or south latitude, 60 degrees north or south latitude, and 90 degrees north or south latitude. That's where the poles are. These are very significant parallels that we will discuss a lot when talking about circulation patterns later in the class. There is one thing you have to be careful of when viewing any flat map like this. Remember, the Earth is a sphere, and so flat maps have to distort things to make everything fit. They often make higher latitudes, areas near the poles, much bigger. If you're curious about latitude and longitude, there are lots of different phone and computer apps that let you explore your position and the positions of other places around the planet. Now let's talk about irradiance. Irradiance is the amount of radiant energy, also known as electromagnetic radiation, falling on a surface per unit area. It's measured in watts per meter squared. It can be measured in space or at an object's surface, that is, at the Earth's surface. Solar irradiance, which is the irradiance for the sun, is often integrated over a given time period in order to report the radiant energy emitted into the surrounding environment during that time period. This is called solar irradiation, solar exposure, solar insolation, or just insolation. You can see irradiance varies significantly with latitude. This map is showing average irradiance for several decades. There is much higher irradiance at lower latitudes, that is to say, at or near the equator. Irradiance depends a lot on the source. There are lots of different types of stars that range in size, heat, and lifetime. Most stars are currently classified under the Morgan-Keenan MK system, shown on the x-axis to the right, ranging from O-type, the hottest, down to M-type, the coolest. Note that the letters are not sequential. The diagram shows a star's magnitude against its spectral type. Hot and bright stars are in the upper left-hand corner, and cool and dim stars are in the lower right-hand corner. You can see there are some cool but bright stars termed giants, and some hot but dim stars termed white dwarfs, but most of the stars, including our Sun, follow the main line. Our Sun is a G-type star. As stars get bigger, denser, and hotter at the center, the rates of fusion rise much faster and the star loses energy quicker, so they tend to burn out faster. Ultimately, the amount of irradiance that nearby objects receive will depend on the type of star. Irradiance also depends on the angle of incoming radiation. This is the angle of incidence, and it is the angle between the surface plane and the incoming rays. The intensity of light changes as the angle of incidence changes. When the angle between the surface plane and the incoming rays is high, such as 90 degrees, which would happen at the equator, the light is concentrated into a smaller area, as shown in the top image. When the angle between the surface plane and the incoming rays is lower, the light is spread out over a larger area. That happens near the poles, and that's shown in the bottom picture. In this case, the radiation will be less concentrated. The angle of incoming radiation is a factor on Earth since Earth is a sphere. The sun is so far away that its rays arrive at Earth parallel to each other. Essentially, all rays are the same distance from Earth regardless of latitude. But the Earth is spherical, so the sun's rays strike different latitudes at different angles. This causes areas near the equator to receive more energy per unit area than areas near the poles, which have a lower angle of incidence. That means the same amount of solar radiation is spread out over a larger area. Latitude is the most important factor determining climate. This means that some latitudinal zones are more habitable than others. These angles change significantly with the seasons, which are caused by Earth's axial tilt. You should note that the distance from the sun is not what causes seasons, it is the axial tilt. The amount of atmosphere also affects the amount of radiation that the Earth receives because some solar radiation is reflected back to space by Earth's atmosphere. The higher the latitude, the lower the angle of incidence, then the more atmosphere that solar radiation has to travel through. This is added on to the fact that the sun's rays are spread out over a larger area. The position and the path of the sun in the sky change with latitude, time of day, and season as well, which affects irradiance by affecting the length of time the sun is in the sky and the angle of incidence. In order to know the relative position and path of the sun, you need to know the sun's altitude, which is its elevation angle, and azimuth, which is the angle from true north. The image on the right shows different paths for the sun at different times of the year. You can see the sun has the shortest path and is situated lowest in the sky on the winter solstice, and has the longest path and is highest in the sky on the summer solstice. We will talk more about that later in this lecture. But it is important to know that the daily and annual path of the sun in the sky affect weather and climate, and thus habitability. Irradiance also depends on the distance from the source. This is called the inverse square law because the change is exponential. Objects closer to the sun receive more energy per unit area. This is why planets closer to the sun are hot and planets further away are cold. The table on the right shows the distances of different planets from the sun and their surface temperatures. You can see that closer planets are typically much hotter than planets further away. The reason why Venus has a higher average surface temperature than Mercury is because the atmosphere is primarily CO2, which is a greenhouse gas. Now that we've covered some of the background stuff, let's dive into Kepler's laws of planetary motion. There have been many people who have made important observations and discoveries that led to Kepler's laws. Here are some of the main players. Tycho Brahe made precise observations of planetary and star motions. Johannes Kepler derived the mathematical laws governing an elliptical orbit. And Isaac Newton proved Kepler's equations using his theory of gravity. This is a great example of the scientific method. People built on one another's ideas by making observations, forming hypotheses, testing these hypotheses, and adjusting hypotheses, and so on. There are 3 laws of planetary motion. The first is that the planets revolve around the sun in elliptical orbits. The sun is one focus of the ellipse, and the other is visualized by the small black dot in the upper image. This means that the distance to the sun changes as the Earth follows its orbit. The minimum distance between the Earth and the sun is at the perihelion on January 3rd. The maximum distance between the Earth and the sun is at the aphelion on July 4th. Again, note that the maximum distance away is during the northern hemisphere summer, so distance from the sun is not the cause of seasons. The second law is that the planet sweeps out equal areas from its orbit in equal amounts of time. This requires that the planet travels faster when it is closer to its star and slower when it is further away. The second image shows blue areas. The time it takes to travel t is the same in each scenario since each of those blue areas are equal. The third law is that the planet's orbital period is determined by its distance to the star. That means the semi-major axis. This law is just saying that the further away a planet is, the slower the revolution. There is a helpful video link here if you want to review this information further. We have said it several times at this point, but Earth's axial tilt, also known as its obliquity, is the major cause of Earth's seasons. On short timescales, like a century, Earth's axis of rotation always points in a constant direction. It does change on very long timescales, but not something that we think about with our lifespans. The tilt of Earth's axis is measured with respect to the perpendicular to the ecliptic. Remember, this is Earth's orbital plane. The ecliptic is also the path in the sky along which the sun slowly travels over the course of one full year against the background of the fixed distance stars, as viewed from Earth. Because Earth's orbital parameters are consistent, so are its seasons. Astronomical seasons relate to Earth's orbital motion and are defined by the position and time of the solstices and equinoxes. It is different from meteorological seasons, which follow the annual temperature cycles. Put another way, astronomical seasons follow the position of Earth in relation to the sun. As we have already noted, the Earth is closest to the sun in January, yet it's winter in the northern hemisphere. The seasons are switched in the southern hemisphere. That is because the axial tilt, also known as the obliquity, causes the seasons. The June solstice, shown on the left, is the summer solstice, the longest day of the year for the northern hemisphere, and the winter solstice, the shortest day of the year for the southern hemisphere. You can see that because of the tilt, areas in the northern hemisphere are illuminated more as the Earth rotates. The December solstice, shown on the right, is the winter solstice for the northern hemisphere and the summer solstice for the southern hemisphere. Again, because of the tilt, you can see that areas in the northern hemisphere are not illuminated very much as the Earth rotates during this time period. We have covered enough background info that we can now talk about latitudinal geographic zones. These are special parallels with distinct climatic conditions. The Earth is actually divided into 5 distinct latitudinal geographic zones. These are the Arctic zone, or the Antarctic zone if you are in the southern hemisphere, the subarctic zone, or the subantarctic zone, the mid-latitude zones, the subtropical zones, and the equatorial or tropical zone. Remember that higher latitudes experience drastic differences in temperature with season due to the axial tilt, so the Arctic and subarctic zones, or the Antarctic and subantarctic zones, will change a lot with season. Mid-latitude zones change quite a bit too, but not quite as much as the higher latitudes. Understanding how to estimate climate based on latitude will be an important concept that we will revisit in this class. Here are a series of images that show how varied the sun's path and thus insolation is depending on latitude. Remember that solar irradiance is often integrated over a given time period, and this is called insolation, among other things. At the equator, the sun is highest right overhead during the equinoxes, but there is high insolation year-round. Then at 40 degrees north latitude, the sun is highest in the sky during the summer, and there is higher insolation at this time. The sun is lowest in the sky during the winter. This would be the same for 40 degrees south latitude, you just have to swap the dates. At the North Pole, the sun is visible but low in the sky during the summer. For a period of time, it is visible 24 hours a day. Then the sun is low in the sky and not visible at all for a period of time during the winter. Again, this is the same for the South Pole, you just have to swap the dates. Here are some helpful videos for understanding seasons if you want some additional info or need help going over the material again. So let's sum up the many orbital factors that affect Earth's climate. First is the distance to the sun. The size of the ellipse determines how far Earth is from the sun. We've already talked about how things further away from the sun receive less incoming solar radiation. A factor that affects this is the eccentricity of Earth's orbit. That is, how different Earth's orbit is from a circle. It is a little different though, so we will call it the second factor. Third is the obliquity of the ecliptic, or the axial tilt. This affects the seasons. Fourth is the timing of the seasons with respect to the perihelion. The technical term for this is the precession, and it is the wobbling of Earth's axis. These factors, eccentricity, tilt, and precession, vary naturally on extremely slow time cycles, known as Milankovitch cycles. Currently, Earth's eccentricity is near its least elliptic, its most circular, and is very slowly decreasing in a cycle that spans about 100,000 years. Earth's axis is currently tilted 23.4 degrees, or about halfway between its two extremes, and this angle is very slowly decreasing in a cycle that spans about 41,000 years. The changing of these three factors causes ice ages to start or end, and can cause the Sahara to be green or a desert. But it's important to point out that Milankovitch cycles are very slow and do not affect the orbital configuration, seasons, insolation patterns, and climate over short timescales, ones that are relevant to humans. That concludes the material. Let's go through and review the main points. Astronomical factors for planetary habitability are very important and fundamental. Earth is part of the solar system and the Milky Way galaxy. The sun is powered by nuclear fusion, turning hydrogen into helium. The rotation of Earth on its axis causes the day-night cycle. The sun and moon affect tidal cycles on Earth that depend on orbital periods. Solar irradiance affects climate and depends on the power of the source, the angle of incidence, the amount of atmosphere the radiation has to travel through, and the distance from the source. The discovery of Kepler's laws of planetary motion is a great example of the scientific method. Kepler's laws are that planets orbit in ellipses, with the sun as one of the foci, planets sweep out equal areas in equal amounts of time, and the period of a planet depends on the size of the orbit. Earth's axial tilt causes the seasons, and there are large variations in insolation across the globe according to latitude and season. 4 astronomical factors affect Earth's climate: distance to the sun, eccentricity of its orbit, obliquity, and the timing of the seasons with respect to the perihelion, also called the precession. The latter 3 vary over thousands of years and can affect climactic cycles like glacial cycles. Thanks for sitting through the lecture. To test your learning, I suggest you review the material and make sure you can answer these questions. And these questions as well.